All right, so this video is going to be coming from section 5.2 of the Larson Calculus book, and these were some of the questions that were asked. I'm going to do 41, 45, 63, 73, 95, and 97 in this video. Let's start with 41. Number 41 asks you to solve the differential equation. So if you're asked to solve a differential equation, it's basically asking you to take the derivative and find the original function. So I'm given dy dx and I'm trying to find y. We're also given an initial condition. The book actually also asks us to graph it in your calculator and find 3 solutions. I'll talk about that at the end when we get there. So if we start this problem off, you can probably tell this is going to be a u substitution problem. So my u is going to be 2 minus x. And actually, I'm going to go ahead and write the integral. So I'm like taking the integral of both these sides so that I can figure out what dy is. And actually, we haven't really done this yet, but I'm kind of jumping ahead. Notice if I multiply the dx over there, it looks more normal. It looks like that. And if I take the integral of this side, I get y. And now I'm just trying to evaluate this. That actually is kind of our next unit about separating differential equations, but don't worry about that just yet. So we need to take the integral of this. If u is 2 minus x, then du dx is going to be negative 1. So du is negative 1 dx. Now if I look back over at the integral, notice that this 3 is actually a coefficient. I can move it to the front. So I'm going to put that 3 in the front. And then I have that'll leave me with a 1 on top. Okay, so I'm here, and then if I look over at my du, I need a negative 1 there, so I'm going to put a negative on the inside and a negative on the outside. So again, I'm not really putting it there, but I'm multiplying by it. Now I can do substitution. So negative 3, the integral of 1 over u du. Of course, that's our lovely natural log rule that we already know. C. So I have y equals negative 3, the natural log of 2 minus x plus c. Now we actually are given an initial, well, not really an initial condition, but we're given a condition, like we're given a point that actually is on y, so we can plug that in. If I plug in the point into x and y, the point was, sorry, I lost my place. The point was 1, 0. So I'm going to plug that in. 0 is the y. 1 is the x. And then here's the ever popular natural log of 1, or log of 1. So the natural log of 1 is actually 0 because e to the 0 is 1. So I just found out that c is 0. So like the actual solution for this problem is y equals negative 3 natural log of 2 minus x. That is the solution. Now as far as graphing it goes, you would basically just graph this function right here in your calculator and put different values of c in to make it look like just a few different possibilities that could be the solution, because when you take the derivative of it, the c is going to go away and you'll end up with what we started with. So the actual solution is the one that is over here in green, and then this is kind of the general solution. So if I graphed that in the calculator, and this is a really, really rough sketch, you know, you could have something that looks something like this, and one that looks something like that, and one that looks something like that. And the one that is the right one is the one that goes through that point 1, 0. They're just kind of wanting you to notice like the different possibilities that you could start with if you took the derivative of, and what you would start with so that you could end up with that particular dy dx. All right, so number 45 asks you to find the particular solution given the initial conditions, which means we're eventually trying to find f of x. And since I'm starting with f double prime, that means I'm actually going to have to take the integral twice, but we'll do it once at a time. And since we've kind of been in u substitution land for a while, you might be tempted to do u substitution here, but just before you actually do it, notice that if you make x squared be your u, then your du is going to be 2x, and you don't have another x in there. So let's not forget how to do the easy integration. Rewrite it. This is the same thing as 2 times x to the negative 2. And so I can actually just do the power rule for this. So if f double prime, if this function on the inside is f double prime, then it's going to give me f prime, right? Like taking the integral, I'm going backwards. So if I do the power rule to this, I'm going to get that f prime equals 2 times x to the negative 1 over negative 1 plus c. So I'm going to rewrite that a little bit. So that's going to be negative 2 over x plus c. The first thing we need to do is use our initial condition that is dealing with f prime. So I just circled it up there in red. F prime of 1 equals 1. So I'm going to plug in a 1 and plug in a 1 and solve for c. So notice that's negative 2, and if I add it to the other side, I get 3 for my c. So that means that f prime equals negative 2 over x plus 3. Now I need to take the integral again, because the integral of f prime is going to give me f. Now for this one, we don't really need to do u substitution because it's just an x, but remember I can kind of treat this separately as two separate integrals, like negative 2 over x dx plus the integral of 3 dx. You don't have to write that step if you don't want to, but you can. That negative 2 is really just a coefficient, so I can pull it out in the front. And then the integral of 1 over x dx is the natural log of x. And then here, the integral of 3 is going to be 3x. And then I have my plus c. So this equals f of x. I have another initial condition at the top, and that was that f of 1 equals 1. Just circled it in yellow. So I'm going to plug in 1 into my y and plug in 1 into my x and solve for c. Here it is again, the good old natural log of 1, that equals 0. Please know that. Okay, so if I solve that, negative 2 times 0 goes away, I have a plus 3, I'll subtract 3, I get negative 2 equals c. So my function, which I'm going to write in green here, my final function, is negative 2 natural log of the absolute value of x plus 3x minus 2. Ooh, and I just realized at the beginning of the problem, I don't think I wrote it on here. Oh, I did. Do you see at the beginning of the problem it says x is greater than 0? So what that means is I don't really need those absolute value signs there, because x is going to have to be positive, because that's what we stated at the beginning, like that was the domain. So I really could do that in white. Ta-da! Okay, I really wanted to do 63 because it's actually super easy and you probably just forgot from last unit, but this is the second fundamental theorem of calculus. Notice it's asking us to find f prime. If I find the derivative of an integral, remember that they're inverses of each other. So basically all I'm left with is whatever is in here. I just need to plug my bound in. So the answer is 1 over x. That is it. That's all it is for 63. Now, you didn't ask for this one because we didn't have it on our homework, but if we look at 65, it asks us to do the same thing, and I just wanted to remind you that if you have something in the bounds, you have to do the chain rule. So if I have to find f prime of this, I'm going to plug in that 3x just like I did before, but I need to make sure I do the chain rule, so it's going to be times 3. Number 73, I know somebody asked for 71, but 73 was asking a similar question, and I thought it might be good since it had some trig in it. So number 73 asks us to find the area of the curve that's bounded by these lines. So x equals 0, x equals 2, and y equals 0. So the x equals 0 and x equals 2 is like our integral bounds. Y equals 0 is just the x-axis, so that's just like them saying do a normal integral, because the area under the curve, you know, up until the x-axis is what the integral is. So I'm basically finding the integral of 2 secant pi over 6x. dx from 0 to 2. If you look at this, remember that pi over 6x is inside the secant function, so that is like my u, which means my du is going to be pi over 6, and so pi over 6 dx is du. So I'm going to replace that, and in yellow I'm going to write a little pi over 6 in here next to the dx. So that's outside the parentheses multiplied by the dx, which means I need to multiply a 6 over pi on the outside of the integral. And then I also can take this 2 and multiply it out as well, and just kind of like take it out. So it's going to be 12 over pi, the integral of secant u du. I'm not putting bounds on it right now because I have u's instead of x's. We could find new bounds if we want. I don't know if it really makes things a whole lot easier or not. You could just find the integral and then substitute in, or you can find new bounds. So if you want to find the new bounds, that would be u equaling pi over 6 times 0, so that's still 0. And then u equaling pi over 6 times 2, which is 2 pi over 6, which is pi over 3. So if I want to do the new bounds thing, the u bounds, it's going to be going from 0 to pi over 3. The integral of secant is the natural log of secant u plus tan u. And that was just one of our new rules that we learned a little while ago. And I am not going to put the plus c because I'm going to be evaluating this from 0 to pi over 3. Because I found new bounds, I don't actually have to substitute back in the pi over 6x for the u. I can just plug in pi over 3 and plug in 0. Okay, let's remember some trig here. So I didn't have to multiply that 12 over pi in, by the way. I could have left it out in the front. Pi over 3, if we think about the unit circle, is over here. The secant is 1 over cosine. Cosine of pi over 3 is 1/2. So the secant of pi over 3 is 2. The tangent of pi over 3 is sine over cosine, which is that. And I'll simplify that in a second. And then the secant of 0, cosine is 1 at 0, so 1 over 1 is still 1. The tangent of 0 is 0. So surprise, surprise, we have our favorite natural log of 0 over here, or sorry, natural log of 1. So that whole thing, the natural log of 1 is 0, and 0 times 12 over pi is 0. So that whole thing is 0. This is 2 plus the square root of 3. And I think that's actually it. Yeah, I mean, you don't really need the absolute value at that point because 2 plus the square root of 3 definitely is positive. If you were to type that in your calculator and get an approximate answer, you would get 5.030, and that's the answer. Okay guys, so number 95 is actually an average value. It says find the average value of the function. When you see that, I'm really hoping you remember from last unit the average value is 1 over b minus a, the integral of a to b of f of x dx. That's the average value of a function. So this is wanting the average value of this particular function from 1 to e. So it's going to look like this. That's supposed to be an e minus 1. So 1 over e minus 1 of the integral of 1 to e of 2 natural log of x over x dx. So when you're looking at this integral, I would say hopefully you notice that the u should be the natural log of x, because if you take the derivative of the natural log of x, you get 1 over x. And in our problem, we have a 1 over x. So right here, and technically I could take that 2 and put it out here. So 2 times 1 and have a 2 right there. And then if you imagine having a 1 here, there is my 1 over x right there. So it already has 1 over x dx in it. So I'm going to have 2 over e minus 1 of the integral of 1. Oh, I'm not going to put my bounds yet because I'm about to put u's in here. So my u is the natural log. So I just put u. And then the 1 over x dx is my du. So I just have this. You would be, again, welcome to go ahead and take this integral and then substitute back in and use the old bounds. Or since I have u's, I can find some u bounds. And I think it'll save us a little bit of time. So the natural log of 1 is our favorite, 0. And the natural log of e is also another favorite. What's the natural log of e? I hope you said 1. Okay, so it's 1. So the bounds go 0 to 1. And I have 2 over e minus 1. The integral of u, that's just u to the 1 power. So I just do a good old power rule. It's going to be u squared over 2. And I'm going to be evaluating that from 0 to 1. So that's going to equal 2 over e minus 1. I think I'm just going to write that once and put it on the outside of the parentheses of 1 squared over 2 minus 0 squared over 2. So I get 2 over e minus 1 times a half. And my 2's are going to end up dividing, and I just get 1 over e minus 1 as the average value of that function from 1 to e. All right, for our last problem, we have a classic bacteria population problem. This is the rate at which the population is changing, this population of the bacteria, and they ask you to write an equation that gives the population at any time t, and they state that the initial population when time equals 0 is 1,000. So this really reminds me of your last test, actually, because it's kind of just like putting this into context. So the population with respect to time, if this is the rate, then I need to do the integral of it to find the actual population. Now what I'd like to do, actually, instead of putting t, I'm going to put x, because I want my integral to go from 0 to t. And it's just proper notation to not have those be the same variable. So I'm going to have an x like in the integral, and then I'm going to put a t there. So that's the population from 0 to t. But as many of you guys know from the test that you got back just recently, I'm missing something. This is just how much the population is going to change from 0 to t. It's like the displacement, the amount that is added or subtracted from the population. So that means to find the actual population, I need to add 1,000 to it, because 1,000 is my initial condition. So I'm starting at 1,000, and then like this is how much it changes, and that will give me my total population. So it asks for an equation to represent the population. So there it is. It's that whole thing. And then it wanted to know what the population was after 3 days. So I would find the integral from 0 to 3. I'm actually going to have to evaluate this integral. So I'm going to pull the 3,000 out so that, hold on, technical difficulties, there we go. So that I can just look at this a little easier. And this is really not liking me at the moment. Okay. The u is going to be 1 plus 0.25x because that's in the denominator. If I take the derivative of that, I get 0.25. Okay, so looking back at my integral up here, if I multiply the inside by 0.25, 0.25 is 1/4. So that means I need to multiply the outside by 4. So let's look at this. So this is going to become 12,000, the integral of 1 over u du, plus 1,000. We could either find new bounds or we can do substitution later. I've kind of just been finding new bounds, so I guess let's do it. I'll do it off to the side here. New bounds or u bounds, whatever you want to call them. New bounds, new u bounds. U is 1 plus 0.25x, so if I plug in 0, I just get 1. And if I plug in 3, I get 1.75. So my new integral is going to go from 1 to 1.75. Assuming this would be a calculator question. If I take the integral of 1 over u, I get the natural log of u. And don't forget that I have that plus 1,000 at the end. $12,000 times the natural log of 1.75 minus the natural log of 1 plus 1,000. So notice I did not plug in my u back, like I didn't plug in 1 plus 0.25x because I found new bounds to go with the u's. So they just really love the natural log of 1, clearly. It keeps showing up. So the natural log of 1 is 0. So this is just the natural log of 1.75. And then I'm going to add 1,000 to it. And if you type all that in your calculator, you get approximately 7,715 bacteria. Yay, the end. I feel like you should see my work setup right now because I find it kind of funny. So here I am, just chilling on my bed. Turns out my pillow's a good desk for the iPad. All the calculus books. Hope you guys have a good night.